Okay, so here's an actually loaded element in tension. So it's being pulled. And what we're going to do to represent this pulling force is a series of sticks whose the dimension of the stick is proportional to the magnitude of the force. So we got two possible forces in here. So we start off by having this element that is under tension only. We'll not ignore the fact that there is a table here, there's no friction, this is just hanging up in the air, and so we have a horizontal force acting in here, another horizontal force acting in here, and is presumably in equilibrium, doesn't move. Okay? So now, here's what we're going to do with it. These are exterior forces to the element, and we're interested in calculating the interior forces in these elements. So here are the options that we got in order to calculate interior forces. So here's the same element that we just saw, and here's the exterior force, nice and horizontal, and we're going to cut. The cut is going to be orthogonal, perpendicular to the element itself. So here is. The question for the students is, so here's the exterior force, we're coming out with the interior force where the cut happens. The question is, out of these three, I hope they are visible, three errors that are available, which one is going to be sufficient to keep this piece in equilibrium? So if you ask the student, is the little one going to keep it in equilibrium? No. Is the middle one going to keep it in equilibrium? No. Then is the bigger one going to keep it in equilibrium? Possibly, if that longer one is in the same direction as the exterior force, so it has to be nice and horizontal as well. So that keeps it in equilibrium. Question is, what type of forces are acting on this cut? And the answers, possible answers is, well, there's a normal force, an interior normal force. There is a zero shear force to maintain equilibrium. All right. So the other possibility to obtain the interior force is that now we come and we cut at an angle. So here's the element, here's the exterior force, and the questions are, what type of force needs to be applied in this cut to maintain equilibrium? So the possibilities are, again, three. You take the small force, probably not, it's not going to maintain equilibrium. You take the middle one, probably not, it's not going to maintain equilibrium. To the bigger one, yes, probably that does maintain equilibrium. The question is, how do you orient that force so that equilibrium exists? So do you orient it this way, do you orient it that way, do you orient it that way? The answer is, well, you orient it horizontal, just the same way that the exterior force is to maintain equilibrium. So now the question becomes, so what are the interior forces in this cut? Do you have a normal force, or do you have an interior, do you have a normal force, or do you have a shear force? And the answer is, well, you have neither one of them. You have a force that is neither normal nor shear. So can you break that interior force into components such that you have a normal and a shear force? The answer is yes. One of them will look like this, the other one will look like that. And so now you do have a normal and a shear force in that element. So now the question can become is, what if we had cut with a different angle? What type of, are we going to get a different answer? Or let me just back up on that too. Are the interior forces in this cut the same as the interior forces in that cut, the shear and normal? The answer is going to be no. There are different sets of normal and shear and different set of normal and shear. But so what are the internal forces in the element then? That's the question that can be asked. And what will happen if we had cut with a different angle, different from that or different from that? Are we going to get another set of normal and shear force?